the idea is really that you see all of this in a space of 8 hours. So hopefully I'm refreshing some materials that you've seen previously. Hopefully I'm putting all of these concepts and theoretical foundations into the same framework and pulling them together. So let's see how the normal linear models relate to all of the things that we've been talking about before. So let's assume that the situation is that we've got some random variables x1 through xk, and we've got another random variable y, and we want to say something about y by looking at the values of x1 through xk. So we want to find some function g that takes the random variables x1 through xk and approximates the values for the random variable of y. So that's really the general case. We'll have a look at a much simpler case. So for the moment, let's assume that we only have one single random variable x, so k is 1. So we've got 1x. And let's assume that this function g is really a linear function. So we've got an expression of ax plus b, slope in x plus intercept. So can we assume that x and y have a linear relationship? That's sort of the first thing that we need to check. So we can check that the easiest by first drawing a scatter plot of x and y. And sometimes it's not x and y that have the linear relationship. Sometimes we need to transform one of them or both to get to a linear relationship. So all of that counts. Let's have a look at an example. So I've got a your turn here, but maybe at the moment you're a bit your turned out. So let's just go through this as an example. So let's assume that we've got some data on the mileage of cars. So MPG is a data set that's inside the ggplot2 package. And one of those variables in the MPG data is CTY, which gives an estimate by the company of by the car makers of how far on average we can drive. So how many miles we drive on average with 1 gallon of gas. So that's CTY, that's city mileage, and DSPL, displacement, so that's the total volume of all the cylinders. So if there's big cylinders in our car, there's a lot of displacement, so it's a powerful car. So we've got displacement, and we want to see what the relationship between displacement and city mileage is. What do you think? Positive? So displacement goes up, mileage goes up. Displacement goes up, mileage goes down. What does your intuition say? Hopefully it says that powerful cars usually have a lousy gas mileage. So let's see whether that is actually true in the data. So the data is a little bit old. I think it's just 2007, from 2007, but I don't think that generally that much has changed in the recent years. So we plot a scatter plot of displacement on the x-axis and mileage in the city. So here's a car that drives 35 miles on the gallon in the city. That's pretty nice. So what we see is a general negative relationship. So as displacement goes down, mileage in the city goes down, but it's not a completely linear relationship. So we might see a linear relationship maybe up to a displacement of 5, and then it seems to be more or less straight. Alternatively, we could say that there's a inverse relationship. But definitely, so when we draw a smooth through the data, we see that this is not necessarily a linear function. So one idea for a transformation would be to use the inverse, so 1 over displacement instead of displacement itself. Let's see how that looks like. So we use 1 over displacement. We plot another scatter plot, and you can see maybe this is a little bit more linear, so we draw a smooth through that, and that looks pretty similar to me. What I find a bit disconcerting is these larger outliers, these larger values away from the line for higher values of 1 over displacement. We'll come back to that, why this is a little bit concerning, but generally the overall structure, that looks like almost like a straight line. So we found a linear relationship between city mileage and a variable 1 over displacement. So how do we find these values of A and B? So generally, I think we can agree that we've got approximately this linear relationship. The next question is, how do we find the slope? How do we find the intercept? So the idea is that we want to find a line. So we've got a line here. Let's start with any odd line. So we start with a line and we look at the distance, or no, I should say the difference, the vertical difference of each point to this line. So each one of these little blue lines, we look at these blue lines, we square this difference between the y value, so the difference between the city, between the actually observed mileage in the city, and the value that we would expect based on this functional relationship in 1 over displacement. So we look at this expression here, y1 minus, this is the function, the linear form that we've got, so axi plus b, we subtract that from yi. We square that difference, we sum over that difference. So that gives us some quadratic form in A and B. And now we can find estimators for A and B in a way that this expression is minimized. So we want to find that function that minimizes this quadratic form. And because this is, so this is called the least squares approach, and A and B are then least squares estimators. So we find slope and intercept as least squares estimators based on this quadratic form. I'll spare you the calculus. We can actually explicitly calculate these estimators, but let's use R to actually get these estimators out. So we're running a linear model, and we have our response variable y, CTY, and now we're using a formula. So y tilde, and we're looking at, we're putting in the covariate here, so the inverse of the displacement. And we get a summary of this model. So this is only a part of it. R is very verbose for summaries of linear models. So let's ignore those for right now, and let's only focus on these values here, the estimates. So that's A hat and B hat. So A times X plus b hat. So how do we interpret those? So 7.3, that is the intercept at which this blue line crosses the value that the blue line takes when the x value is equal to 0. So inverse of something, we can't get to a 0. So we reach the intercept when 1 over displacement is 0. So obviously that's a bit questionable. So we can't really interpret that. So always make sure that when you have estimates that you always question whether you can interpret the parameters directly. So obviously here, the interpretation of the intercept is a little bit questionable. So let's not consider this for right now, and instead focus on this estimate of 28.7. So the way that we interpret this is that on average, we see an increase of 28.7 miles per gallon, so an increase in mileage with an increase of 1 unit of 1 over displacement. So that comes again with a little bit of a problem, because when you have a look at the actual range of 1 over displacement, it's between 0.2 and 0.7. So 1 unit is something that we don't actually see. The difference in mileage is given as from somewhere just over 10 to about 25. So maybe instead of talking about 1 unit increments, we should talk about 0.1 unit increments. So as 1 over displacement increases by 0.1, on average, the mileage increases by 2.87 miles per gallon. So that's pretty good. So that's the slope that we see on this line. So one way to measure how good this line is given by the so-called R square. So R square is reported in the summary that R gives us in 2 ways: multiple R squared of 0.7118, and then an adjusted R squared. So what is R squared? I'm sure that all of you have heard about R squared. And the name of R squared is actually the coefficient of determination. I have no explanation for that. It's a weird name. So R squared is the coefficient of determination. And what it does is R squared measures how much of the total variability in the response variable is explained by the predictor variables. So are explained by the covariates in X. So R squared is actually a ratio. It's the ratio of the total sum of squares minus what's left over of the sum of squares after we do our regression, after we run the linear model. And then we compare that ratio to the total sum of squares. So that means that this whole ratio is somewhere between 0. So SSE can only be at most TSS. So this sum of square is between 0, and it could be, SSE could be 0. So then TSS, we've got an expression of TSS divided by TSS. So in that case, R square would be 1. So our R square values are somewhere between 0 and 1. I should explain what SSE and TSS, how they are actually defined. So SSE stands for the sum of squared errors. So we calculate an error as the difference between what we've observed and what we would have expected based on the functional form. So yi hat. So we look at the difference, we square the difference, we sum up over all of the difference. Sum of squared errors. And then we've got the total sum of squares. And that is essentially something that's very similar to the variance. So we look at the squared differences between each observation and the sample mean of those responses. So how far away, how much spread do we have in our response variable y? If a lot of the spread is explained by the linear model, then we will see very small errors here, which means that this is very small and TSS over this TSS is going to be fairly big. So R squared is between 0 and 1, and a larger R squared indicates a better linear fit. So how much R square is good enough? How little can R square be to be still an acceptable model? So if we have a perfect linear fit, either positive or negative, then R square is 1. So essentially that means that y is equal to something like a times x plus b without any errors. So R square of 1 indicates a perfect fit. R square of 0 indicates that there is no linear relationship between x and y. So x contributes nothing to this linear model that the mean of y wouldn't explain already. So depending on, so usually we're in a case like that. So we have some indication because we checked for that ahead of time, right? We did all of our scatter plots, so we've already filtered out a situation like that. So we have some linear relationship between our covariate x and our response variable y. And we assume that, so we measure that in this R square. So sometimes just looking at the R square might be misleading. So sometimes we have a very low R square value. So that would indicate that the model isn't great. And for the model, we might say, yes, it's not a great model. So not a lot of the variability is explained. But it might still be the case that some of the predictor variables might be valuable. So we might already be better than just randomly guessing. So we might be better than this situation where we have predictors that don't explain anything beyond what the mean of y explains. And very often we are in this situation that we have a fairly low R square value, but we have some strong predictors. And that would mean that we're on the right track to explain something, but particularly when the data is collected about human beings, there might be so many other covariates that factor in that we don't have access to, that no model, regardless of how hard we try, no model is actually going to be a great model. So oftentimes the R square of our linear model might not be great. Don't be disappointed when we're dealing with human beings, in particular an R square of 0.3 sometimes leads to people dancing on the table. So it might look like a terrible R square from a statistical point of view, where we want to go for 0.9, 0.995, something really high. But in whenever we're dealing with humans, there's a lot of extra variability coming in, and we might just not have the full picture, so we might be missing a lot of the variables. So individual predictors might still be very valuable. Okay, so let's be a little bit more precise about this functional form here. So far we've said y is approximately ax plus b. So let's be precise and say y is exactly ax plus b plus some error. So plus this epsilon, and let us also assume that we know what distribution this error has. Let's assume that this error is normally distributed. So it's some sort of random noise. It is scattered around 0 with some variance sigma square. So essentially we've got some error that we can't get rid of. The error is scattered around 0. So on average, the error is actually 0. But there's some noise in the data. So if we make this assumption that the error structure is normal, that means we also make some assumption about what y looks like if we know ax plus b. So essentially, this means that y given x is normal. So our assumption is that if we've got x and if we've got y, that if we look at y along each x, so given the value of x, we've got some normal distribution in those values, in those observations of y that are scattered around this particular value of x. So y given x is normal, and that's again a distributional assumption that's directly coming from assuming that the error structure is normal. So that's a direct conclusion for the distribution of y given x. So we'll make use of that. And how are we going to make use of that? We're going to make use of that by looking at, so it's going to allow us to say something about confidence intervals and say something about parameters of the model. So let's have a look at the summary of a normal model again. So this is the same model that we had a look at before with 7.3, these estimates over here. So now that we've made a normal assumption for the error structure, we actually get a distributional assumption here, and that's going to allow us to say something about the probability of these estimates being above 0. So the t-value corresponds to a test of whether a parameter is equal to 0. That's the null hypothesis. If we have this very small value that tells us that this parameter is equal to 0 by chance, by this chance. So this chance is so small that we would say, no, this parameter, we reject the hypothesis that this parameter is equal to 0 quite strongly. So we want the t-value to be high. A high t-value would allows us to say that these parameters, these predictors, so inverse displacement is an important predictor for the city mileage. A second test that we can use is this test down here. So this is now an F statistic. This is a test that none of the predictors in the models are needed. Again, we reject this test quite strongly, which means that at least one of the predictors in this model is a strong predictor. And we already saw that each individual predictor was a very strong predictor. So I talked about confidence intervals. So let's have a look at the confidence intervals for each one of these parameters. So given that we know the t-value here, we could come up with the value for the slope as, or a confidence interval for the value of the slope as a hat plus minus the t distribution with degrees of freedom of n minus 2 times the standard error that we have here. So if you use this formula, you will come up with exactly these boundaries. So why do we look at confidence intervals? Confidence intervals correspond to these probability values. If the confidence interval includes a 0, that means we don't have a significant statement here, so we can't say that the parameter is significantly different from 0. But confidence intervals also allow us to give a range of likely values for the actual parameter of the slope and the intercept. So we can easily get to those confidence intervals by using the model object. We set our confidence level and we run the function confint for confidence intervals. Okay, so our assumption to have normally distributed errors comes with a responsibility. Now that we have this assumption, we need to check that this assumption is also at least plausible. So that means that we need to check for homogeneity of the variance in the residual terms. So that essentially means that residuals should be spread symmetrically in y along the x-axis, along each covariate. So what we see here is that well, the bulk of the data is here. Does that matter? It doesn't really. What we're looking for is whether along the y-axis we see about the same spread. And essentially this, so here we don't have a lot of spread, but we also don't have a lot of values. So what we're looking for is whether the spread for a similar number of values is similarly wide. And we can say that this is true in this first case. And then we have some structure that definitely looks different from what we would, from what we want it to look like. So here we definitely have some structure in the residuals. So sometimes we see structure along a covariate that that looks like there's something nonlinear going on. So here we have this sort of U shape in the residuals. And that might indicate that that we should not only include a linear form of x, but maybe also an x square to get rid of or try to capture this additional structure. So whenever we see the structure in residuals, that is really an opportunity for us to try to make the model a little bit more complex. So that would mean that the model gets better, so it gets closer to the actual data. And our residual structures also looking a lot better. So we want residual structures to look mostly like this. So here in the third line, we've got something where the variance increases with an increase in x. So we've got a little bit of variance on the y for low values of x, and then the variance really opens up like sort of a trumpet shape. In this case, we should think about transforming x before we include it into the model. So something like a log transformation, like we talked about. So look at the structure of y and x, and most likely you're going to find that the structure does not look particularly linear. So these are usually calls for an additional covariate or some transformation that we've overlooked so far. Okay, lots of information. Let's have a your turn. So here we've got data from Australian rock crabs. So those are beasts that are about maybe 3 inches wide. They live on rocks, like the name says, and they are also very, very colorful. So you can see that they look extremely beautiful on these rocks. So we've got data on this. We've got some measurements on crabs, the frontal lip, rear width, carapace length, and carapace width. So have a look at the relationship between these physical measurements. So look at some scatter plots and then fit a linear model of rear width in carapace length. So we want to predict rear width based on measuring the carapace length. And then we want to check the diagnostics. So we want to check these models. We want to check the residuals for their homogeneity by including other variables that we didn't include in the model. So let's run that. I'll give you I'll give you 5 minutes for a start. Let's see how far we come. Have a look at the code in case you're feeling uncomfortable trying it all by yourself. Maybe just have a peek at the code and try to work from there. But just try to see how far you come by yourself. Okay, so investigate the relationship between those physical measurements. We've got 4 physical measurements, and one way to look at a whole bunch of scatter plots all at once is to come up with a so-called scatter plot matrix. The call for scatter plot matrix in base R is pairs. There's a package that allows us to come up with a scatterplot matrix in ggplot2 that's in the ggally package, and it's called ggpairs. So we select whichever variables we want to include in the scatterplot matrix, and then we draw ggpairs of that. So what do we see? So we've got these slightly cone-shaped, carrot-shaped relationships. So I think our first impression would be there's a super strong linear relationship between any of the measurements, between any of the physical measurements that we see in these crabs. It's probably the strongest between width and length of the carapace. And then it spreads a little bit more for the other measurements. But overall, as one measure is higher, the other measure goes along with that. So really, really strong linear relationships. So let's have a closer look at that. The your turn was asking to fit a linear model of RW using carapace length. So we're looking at this thing here. So one of the ones that's not as linear looking, that has a little bit more spread around this line. So we fit a linear model, we'll call that M1. We fit the rear width by carapace length, and this is going to be model M1. So it's always a good idea to include the fitted values and the residuals of a model in the original data, because we've got the yi hats as well as the individual residuals for each observation. So we have fitted and residuals, and now we want to plot the residual structure, so y is resid, along a covariate, the carapace length. And we get this picture here. And I was a bit astonished when I first saw that. So I usually don't see a V structure in residuals. That's definitely the sign that we're missing some really important covariate. So this is not what a residual structure is supposed to look like. So this is one of these plots where you should be going, whoa, what happened? So now we have to figure out what happened. And we already get a pretty good clue by including some color. So here we color female crabs in pink and male crabs in this bluish color. And we see that we now have two lines in the residuals. So one line goes down in blue for the males, and one line goes up in pinkish for the females. So what does that mean? That essentially means that we should probably include gender as one of the covariates in our model. But let's check species first. So let's see whether species has any impact on our residual structure here. So we switch out sex and species. And the coloring is really unfortunate because there's a blue species and an orange species. And obviously the colors don't match that, but it would be really nice if it could match. But the important thing here is there's no structure. So we've got some random scattering of pink and blue dots, and there's no structure. So species is not contributing in a structured way to this random structure, at least not that we see it right now. So we really need to focus on sex and include sex somehow into this model. So how do we expand our normal models? So for right now, we only had a single covariate. So how can we include other covariates? So if we have continuous random variables, the extension is in a linear model is quite straightforward. So we've got not just one a times x, but we just add a couple more slopes and we add a couple more random variables there. Then the least square solution, instead of just having one a and b, we have k a's and b. And this whole thing, extending a normal model from a single covariate to k covariates is not really a problem. It's just a bigger minimization problem. but the estimates, we can find the estimates in exactly the same way. So we minimize this least square sum in now k plus 1 parameters instead of just 2 parameters. So if we've got discrete random variables, sometimes we've got discrete random variables that have the form that go from, that have a form of a Likert scale. So when there's a survey question that asks, how much do you agree with the following statement? And you go from not at all to I don't care to I very strongly agree with it. So we've got some ordinal scale. So rather than thinking about this outcome variable as a discrete random variable, we can assign scores to it. So we can just say that negative, so I disagree might be a -5, and I totally agree is a +5. And then the neutral would be somewhere in between, maybe a 0. So then we can treat these ordinal discrete random variables in the same way as a continuous random variable. We just treat it like a numeric variable, and we put it into the same minimization problem. So, but how do we actually go about with a discrete random variable like gender or species, where we don't have an order? What do we do? So let's see what R is doing. So when we just include a factor variable in R, like this, so we've got now a model where we've got carapace length and sex, then what we get is we have an additional line in this model. It says the sex for male leads to an estimate of -2. So males have this downward line. So as if so, no, sex, no, they don't. They have a negative estimate. So the male crabs are on average -2, but where are the women? Where are the female crabs? So we're sort of missing a parameter here. And what we're missing is that R treats one of the levels as the reference category. So here we're treating females as the reference category, and the reference category is always assigned a parameter value. It's always assigned the value of 0. So this -2 is really a comparison to the female crabs. So compared to female crabs, male crabs are 2 millimeters, have a 2 millimeter lower rear width than the female crabs. And what we can also see is that our R-square value just went up quite a bit, from 0.7 to 0.9. So we included one variable and we got a huge gain in R-square. So we'll keep this variable. It's for sure a good variable to have. We can also see that it's highly predictive. So, but we still need to understand a little bit better how this variable, how R is really dealing with this variable. But let's have a look at how R is actually dealing with these discrete random variables. So let's assume that we've just got a single categorical variable. So it's a discrete random variable. We've got J levels. what we do is we create dummy variables. So a dummy variable consists of ones and zeros. It has the same length as the original variable x. And the dummy variable is either 1 or 0. It's the dummy variable j is 1 if the original variable x has the level j for this particular observation. So this is called an indicator variable. We can write this as di is equal to the indicator. Oh, this is, sorry about this. This x is equal to I. So this is an I. Di is 1 if x is equal to I and 0 otherwise. So we've got this set of dummy variables, and now we've got 0 ones. So if you want to, we can treat this now as a numeric variable. And we include in our model, instead of including x directly, we include these dummy variables and we assign them slopes a2 times d2 plus and so on aj times dj is plus epsilon. That is now our linear model. And note that A1 and D1 are left out. So D1 is used as our reference level and A1 is set to equal to 0. So we have to do that because of estimability. I'm not going to go into any kind of estimability issues, but essentially if you think about the different levels of J, if we add up all of the dummy variables, D1 to DJ, we get a vector of all ones. So that is in our model matrix the exact same way that we write the mean. So we can either estimate the mean or we can estimate all of the dummy variables. But if we try to estimate both the mean and the dummy variables, we have a rank deficiency. So if R is complaining about not being able to estimate something because of a singularity or a rank deficiency, that's exactly what it's referring to. So we solve that issue by leaving out one of the levels or leaving out the mean. But here we're leaving out A1. So the nice thing is R is creating these dummy variables on the fly. We don't have to do anything about it. We get the results. We just need to know how to interpret those results. So if we've got binary variables such as gender or species, then we will only see one additional parameter. And the other one that we don't see is set to 0 as a reference. Okay, so let's have a look back. So -2 indicates that compared to the women, the males have an expected rear width that's 2 millimeters shorter than the female crabs. So let's now diagnose that model and have a look at the residual structure. So we had this V shape, this rotated V shape in the residuals before. Let's see if anything has changed. So we look at the fitted and the residual values. We include those into the data. Now we plot with the exact same command, but the residuals have changed. And our residual structure has changed, but it's still a little bit odd. So now we've got an X. So now we've got a downward, a line going downward for the males and a line upwards for the females. So this is an indication that depending on sex, the carapace length actually has a different effect on the rear width on the rear width. So males and females have different slopes of carapace length for the different genders. Let's have a look at that in the model. So we can have a look at the actual scatter plot. So we observed before that we had a bit of a cone shape, but we didn't use color on it. So we should have probably used color on it, because then we would have seen this effect right away. So carapace length is on the x-axis, rear width is on the y-axis. And we can see that the males have a line, the females have a line, the two different slopes are different. So when we see something like that, that the slope, the effect on RW depends on a interaction between carapace length and gender. So that is an interaction term. So carapace length has a different effect for male crabs on rear width than for female crabs on rear width. In R, we denote this interaction by a star. So a star means we include an interaction term and all of its main effects. A colon means we only include the interaction effect. So here we run our third model now. We include an interaction effect, and you can see that I am now not writing out CL plus sex plus the interaction effect. I'm just writing out CL star sex, and that includes all of these effects. So I've got an intercept, I've got a slope for CL, I've got a offset for male, and I've got a slope for male. I don't have anything for the female, so anything that relates to the female crabs is set to 0. The females are our reference category. So what do we see here? All of the parameters are highly significant, so indicating that they are different from 0. And that's true even for this one. So it's pretty small, but when you have a look at its standard error, the standard error is even smaller. So it's an indication that we really need this parameter, and this estimate is different from 0. How do we use a model like that? Or how do we interpret those parameters? So for a male crab, we start out with an intercept of 0.8. We add 1.8 to that just because it's a male crab. And then we have a look at its carapace length. So let's say we've got a carapace length of 30. That would mean that we take 30 times 0.4 and we take 30 times this negative 0.11. And we add all of these pieces together to come up with an estimate for a male crab with a carapace length of 30. So we get a line that follows this blue lines, and we get a second line that follows those female crabs. Let's have a look at whether, oh no, I want you to investigate this model a little bit. So I'm going to hand over And essentially what I would like you to do is try to run the code for this third model. You can try to find a different way of writing out the parameters and still come up with the same model. But I just want you to play around with the specification of this linear model in R, because I think it's good to get acquainted a bit with how R writes out different parameters, different covariate structures. So again, I'll give you 5 minutes. And then we check in again. Okay, my 5-minute alarm went off. How are you faring? Can you write out the model in a different way? Let's have a look at the solution, the official solution of this your turn. But really the aim was for you to familiarize yourself with the code and just be daring enough to change some of the model specification. So let's see how well that went. So what we're doing here is so here I'm using a model that uses sex and a interaction term of carapace length and sex to predict rear width that includes an intercept. And we have, again, 4 parameters, including the intercept. But we now don't have a intercept. Now we don't have a slope for CL by itself, but now we actually see a slope for the females. So if we now are interested in a line, in the line for the females, we can directly read that off from these estimates. The females follow a line with this intercept, so 0.83 plus 0.4 times the carapace length. So this is the intercept for female crabs and the slope for the carapace length for the females. And then we've got an intercept for the male crabs that consists of the intercept 0.83 plus 1.8, and then a lower slope for the males of 0.28. So we can now almost read off the 2 intercepts, the 2 different lines that we're fitting for carapace length for the 2 different sexes for those crabs. So that gives us the same. So you can check this, the fitted values and the residual values, and they will be the same. We can also check the residual structure here. So we're plotting carapace length along the x-axis, and we look at the residual structure. And for the first time, we actually see no structure in the residual structure, which is exactly what we want to see. And just for good measure, we also include sex in here. And you can see that there's a random, the color is really random among those dots. So there's no obvious structure that we can see in the residuals anymore, now that we've included both a parameter for the sex of the crab, the length of the carapace, and we're looking at also the interaction between carapace length and the sex of the crab. So this looks like a fairly nice model, and the overall model has now an R-square of above 0.96. I'm not completely sure what it is, but if you run summary on model 3 or model 3B, depending on which one you have, you'll be able to read off that R-square value. So what do we use models for? So for all of your projects throughout the summer, you will at some point work with a model, and you will use these models. So these models are really our way to replace any kind of crystal balls. So we want to come up with predictions for future observations or predictions for expected values in a way that is informed by the model. So the only reason really why we come up with models is to come up with predictions. And we're making two kinds of predictions. We can use a model to predict mean responses, or we can use a model to predict a future observation. So the mean response would be what would be expected rear width of a rock crab with a carapace length of, say, 25. That's an expected value, so expected rear width. A different question would be, what would be the rear width of a rock crab with carapace length of 25? It looks like a very, very similar question, but the difference is we're looking either at rear width, the value of rear width itself, or we're looking at the expected rear width. The thing is, the model is going to give us the exact same answer for both of these values. So where's the difference coming in? So we can come up with rear width of, let's say, a male crab with carapace length of 35 millimeters. So slightly bigger crab than what I was just talking about. So we've got a rear width of about a little bit over a centimeter, 12.6 millimeters. So the question then is, what are we interested in? Are we interested in the expected value? Or are we thinking of this value as a future observation? So depending on that, we're going to go for two different types of prediction intervals. We're either going to use a confidence interval, or we're going to use a prediction interval. So the interval for the mean response, so an expected value, is a confidence interval. And we've got this expected value of 12.6, a 95% lower confidence interval, a 95% upper confidence interval. And you can see that the lower and the upper confidence interval are super close. So we already saw that the lines of those rock crabs were really tight. So that's reflected in this huge amount of certainty or this very small confidence interval for the expected value of the rear width. So in contrast to that, if we are interested in the rear width of the crab that we just fished out or just picked up from the rock, and we measured the carapace length, we've determined somehow that this is a male crab. And we're interested in its rear width. Then the best estimate that we can come up with is still the 12.6. But now our confidence interval is going to be a bit bigger. So our confidence interval is going to incorporate additional uncertainty, because this is not an average crab. This is not just an average of rear widths, but this is an actual crab. So it's a single observation, which means that we need to incorporate the variability that we see that comes with a single observation. And the way that this manifests itself is in a slightly bigger prediction interval, so in a bigger interval. And because we just look at a single observation, we're going to call this interval a prediction interval. So this is a future observation. This is not something that we've seen so far. It's a future observation. And our intervals are now, the boundaries are a little bit wider to accommodate for more individual variability. And overall, they're still super small, but we need to include the variability that we see in the line. So we've got this added uncertainty. So this might not look like a huge deal, but it's essentially the difference in terms of what we report to our clients later. So if we want to report the expected value with an interval, or whether we want to report a prediction interval. So and most likely our clients are going to be happier with us if we report the prediction interval, because they are encountering individuals one at a time, and they're going to compare the values that they see with these individuals. They will compare that to the model expectation and look at the interval. And if we compare what we see with the individuals to the mean response, individuals usually don't follow any kind of averages. So we're going to fall outside this interval a lot more than 5% of the time. So that is going to create some distrust in our clients regarding the model. And in effect, it's just a misunderstanding of what we're trying to show. The top interval is talking about the mean structure of the model, whereas the bottom interval talks about a future observation. So this will be a future crab, and a future crab with carapace length 35 for a male crab is going to, so 95 of them are going to have a rear width of between 11.7 and 13.4. And only 5 of them are going to fall outside that interval. So prediction intervals are much larger than confidence intervals. But if we report those prediction intervals, we'll end up with a lot happier clients, because prediction intervals are a lot more accessible and understandable than those mean structure intervals. Okay, so this is the point for me to stop. Thanks a lot for your attention. I know that this was what turned out to be 7 hours rather than 8 hours. So you get an hour of your afternoon back, but I'm happy to stay around and answer any kind of questions that you have. Thanks very much.